Okay, so in this lecture, what we will do, we will discuss the operators for Verilog. This is lecture 2. We will discuss expressions and operators, and let's start by going to our this master slide that shows me the skeleton of Verilog module, which is the basic structure of the Verilog language. So what we're going to discuss here is how I can create these expressions in the assign statement or inside the always block. How can I add things? How I can do the anding, the relations. So we'll talk about expressions and operators. And I must say, in this sense, Verilog resembles a lot the C language. And so you will see me going through this a little bit in a faster pace than the other parts of the Verilog language, because you have seen this. It's similar to other languages, and this is one of the advantages of using Verilog. It resembles in this part, and actually in many other parts, the C language and the C plus language. Okay, so there are in terms of expressions, there are two types. The unary expression, where you have this operator applies on one variable, and binary expressions where the operator operates on two variables. Okay, operands can be either net or a wire. And it can be also a register. Logical expressions return 1, 0, or unknown. Okay, these are the possible values for the output of an expression. Now, arithmetic operators, much like any other language, we have the add. Okay, we have the add. We have the subtract, we have the multiply, we have the divide, we have the power, which is exponent, and then the modulus. Okay, so for instance, here, let's say here you are adding a plus 12. You are adding integer to 12, okay, to uh, uh, a plus 16 bit of the value 12. So here you are adding 16-bit integer, which is this one here, to the variable a. Okay, any operand which has a bit which is a value x, the result will of the expression will be x. So the x, the unknown, is very dangerous in simulation. Okay, so suppose we have these values to explain more. Suppose we have these initial values for the variables a, b, and d. So a plus b, right? It means that we are adding this variable to this variable with these values. You add the bit by bit, and you get this results. Okay, and we have other courses. I'm sorry, we have early in this course how we conduct the addition and multiplication and other operation. B minus A, similarly, very important to understand that whenever we have negative or subtraction, the math typically done in 2's complement. Okay, so here is the division, integer division, modulus operation, exponent, ila akhirih. One thing important, divide, modulus, and the power operator are not supported by most synthesis tools. And basically, this is when you take Verilog code and you try to generate gates. This process is referred to as synthesis. In many of the synthesis tools that are available now, these three operators are not synthesized, which means you have to implement them in more simplistic operations like addition and multiplication. Okay, arithmetic operators, more on the modulus. Okay, all right, there is nothing new here. I would discourage using negative with modulus in Verilog. This is really don't do that. Basically, this is just okay, not very appropriate for Verilog. Okay, Verilog is more bit and byte language oriented. such fancy stuff will generate sometimes, especially the negative one, because negative numbers are typically represented in two's complement. So yeah, you don't know what you are getting basically. So negative 4, it is the to the two's complement of 4. Okay, positive 4. This is the unary operators. Okay, and so this في عندي حدا بيسأل لأني سمعت صوت طلع. Somebody is asking question, or somebody forgot to mute their mic. Okay, so we are done with this arithmetic operators, because really there is no surprise there. And let's go to the bitwise operators. So I can have bitwise of ANDing bit by bit, ORing bit by bit, or inverting a single bit. Okay, so if I'm ANDing bit by bit, so here is method, for example, bit A, and here is bit B, for example. So bit A can have a value of 0, 1, or unknown, or high impedance. And similarly, bit B will be 0, 1, X, or high impedance. So what are the outputs? Well, we know if you have a value of a 0, you can always expect the results. If one of the variable is a 0, you can expect the result to be a 0, right? But if the two variables, if the two bits are ones, then the result would be 1. If any of, and this is the new thing for you in this course, if any of the bits that I am ending is high impedance or unknown, you will get unknown as a result. Okay. I get many times questions from the students when they simulate their code that why we are getting unknown. Well, because you have the input of that gate, one of the variables unknown, so it propagated the unknown to you to the output. Okay, so this is excuse me, this is the ANDing of bit by bit. How about the ORing of bit by bit? Okay, so the ORing of bit by bit, if any of the bits is 1, okay, then the result will be a 1. If the two bits are zeros, then the result will be 0. Otherwise, the result will be X. Okay. Now, if I'm inverting using the not here operator, okay, and this is the symbol of it, the squiggly here, okay, then, and this is the symbol of the OR, and this is the symbol of the AND, okay. If I'm doing the not here, then the 0 becomes a 1, the 1 becomes a 0, the high impedance and the unknown will produce unknown value at the output. Okay. Now, here's an example, right? I'm doing in this example what? I want to do so this is the value of 5. I'm sorry, the value of X, which is 4-bit of this value, and value of Y, 4-bit of this value. So I want to do what? I want to do OR bit by bit. So here's the way to do it. So I'm gonna see if so I'm gonna OR this 0 with this 0. So 0 and 0, the result will be 0. Okay. Now, and I'm gonna OR this 0 with this 0, and the result will be what? A 1. Okay. And then I am going to OR this 0 with this 0, and the result will be a 0. Okay. And then I am going to OR this 0 with this 1, right? And the result will be a 1. This is how I do a bit by bit ORing. Now, look at the second example here. And the second example here, I have, let's see, in the second example here, I have, okay, I have a ORing, but this ORing is different than this ORing. This is a logical ORing, and we will study it in the next slide. But what this slide is saying that this is not the same as this. Because in the logical ORing, what do? I look at X and I see a value. I said, okay, this is a value. This X is not a zero. Then it's a true. Okay. Or with this value of a Y. Y is a value of a zero. So true ORed with false, the output will be what? True or 1. Okay. Now, why did it consider X as a true? Because any variable which has a value non-zero, it is considered to be true. Any variable which has a value of a zero, it is logically considered to be false or zero. Okay. So this is not bitwise right here, the operator. That's why you have two different results. Now here is an example of a bitwise. You can see that here we are doing an implementation of I'm NANDing these two bits, and then I'm ORing the result with bit D, and then with bit A I'm doing an OR, and then producing a Q. So obviously you have A, B, C, D are the inputs, all right, and the Q is the output, and this entire thing is expressed in this expression. Okay, and notice these operators that I'm using. Those are bit operators, right? Bit operators, because I'm doing a bit operations here. Now, a reduction operator, um, it takes the value of multiple bits and apply an AND, apply an OR, okay? Because it takes multiple bits and generate one bit. We call them reduction operators. So how do I have an AND? Let's say, for example, this is a bus which is a bus. How do I do an AND? So let's just take the eraser. Okay, let's go to the pen. So this is how I apply an AND operators. So let's say this is what this is a bus. I want to apply an AND. Okay, so this will be something like this here. So what have I done here? I applied an AND reduction operator, which is an AND gate, basically, right? An AND gate on the bus A, right? And I produced what? A Q1. So this is the output is equal to Q1. Okay, so and similarly you can do for the ORing. This notation is an XOR. Okay, so here here is an XOR. This notation is an XOR. This is a NAND, a NOR, and an XNOR. Okay. All right. So here, here it says that basically we apply, suppose X is this, and we apply on it the AND reduction. Obviously, the output will be 0. How about the OR reduction? Obviously, since I have one of the bits 1, it will output with 1. How about the XOR? So you XOR and you get results, and this is because you have even number of ones. You get an output of a 0. Any questions here? Logical operators, they are different than the bit operator. Watch, we repeat the AND operator like so to differentiate between the logical and the bit by bit. Okay, so this is logical, and this is the exclamation mark is considered to be the not for logical operator. Now here the logical operator, when I do ANDing here between this variable and the A and the B, or the ORing, or the so these variables will have either a value of a true or a value of a false, and the result of the logical operator will be a value of a true or a false, and the true is considered to be 1, false is considered to be a 0. So for example, let's take a look here. What we are doing, I'm ANDing A, which is a value of 3. So a value of a 3, any non-zero value is true. So this is true, A is true, ANDed with B, which has a value of 0, ANDed with false. So true ANDed with false will be false. So this is false or a 0, the output will be. How about if I do logical ORing? 0 and a 1. it will be a 1. How about the inversion of A? A here is what considered to be a true or a 1 because it has none value logically. So if I invert it, it would be a value of a 0. And B has a value of a 0, so it's considered to be a false or a 0. So if I invert it logically, it will be a value of a 1. Of course, any unknown will produce an unknown result. Okay. Okay. So here I can do an expression here. So I'm doing logical ANDing here of what? I'm checking here if A equals 2. Is A equal to here? No, equal A equals. So this is a false. And if is B equal 3? No, B equals 0. So this is a false. So false added with false will be false. Now, okay. Now, logical operators, as I said, they apply they consider the the operands as 0 and 1. So, for example, I'm doing a logical operation on these two values. This is considered to be true because it's not equal to 0, and this is considered to be a true. It is not a 0. This value is not a 0. This value is not a 0. True ANDed with true equals what? True, and true corresponds to a 1. Okay. Similarly here, you can you have here A and B. All right. A has a non-zero value, so it's a true. B has a 0 value, so it's a false. The inversion of A is false because A is considered to be true logically. The inversion of B is true because B is considered to be false logically. If I AND logically A and B, I'm ANDing true to false. The output, it will be a false. If I'm ORing a true to false, true to false. This is true. This is false. Okay, so the output will be true or 1. Okay, so I'm done with the logical operators. Okay, and then I will move to the relation operators, and this is exactly what we have in C: greater than, less than, greater than or equal, like any other language. So I'm not going to spend too much time on it. So you can look at these examples. Okay, we have the equality operator, which is A equals B, which is basically it is true if the value of A equals the value of B. All right. And A is not equal to B. It is true if the value of A is not equal to the value of B. So these are relational operators. These are relational. Okay, greater than or equal or greater less than or equal, but these are equality relational. Okay. If I have 3 instead of 2, 3, it will allow me to consider the x's. So this value is equal to this value. This will be true. But if I have only these notations, right, the x's, right, will result in an x in the relationship. So these notation will consider comparing x to x, but the one on the top here will not consider x's in the relation and will result in an x in the relation checking. Okay. So these will consider comparing x's and z's. Okay. So here are the equalities and not equalities. This is equality with case sensitive, which means we'll consider x and z. Okay. So here's an example here. Okay. So let's see if I have this A equals this and B equals this, right? Now, is A equal to let's see if A equal to this 4-bit value, and if you check it, right, the A is equal to this 4-bit value, so the result of this expression is true. But is A not equal to this? No, the A is equal, so A is not equal is a false. Okay, all right. Now, here is the value of b, the value of b here, which is 101x, the value of b here. So is b equal to 101? No, because these two notation cannot compare x's, so you will get unknown. But these notations will consider x's. So here it will give you a 1, and here it gives you a false when you match or you don't match. Okay, so these notations will allow you to compare the x's and the z's. That's why we call them case equality. Okay. Now, done with the relation operators, relation operators, greater than, less than, equality, and now to the shift operators, which is basically we are shifting. I believe Uh, probably that's okay. So, yeah, one or two topics. So the shifting, much like any other language. Okay, we shift. Let's get an example here. Okay, so I have, this is the value of x, right? 1100. We talked about shifting in our course earlier, but let's just check the notation. What do we have here? What does this tell me? This says that shift x, which is the variable x, the variable shifted by how many bits? Shifted to the to the right 1 bit position. And if we do, then this will be the output, 1 bit position, right, to the right, and assign the value to a y. Now I want to shift not to the right. I want to shift to the left, 1 bit position. Okay, so this is 1 bit position. I want to shift to the left 2 bit positions. Okay, and this is shifting to the, so this is a shifting operators. Okay, um, where this is the syntax. This is the variable. This is how many bits we are shifting to the right or to the left. Okay, now shift arithmetic is by adding one of these greater thans or less thans, then the shifting becomes shifting arithmetic, and we know the shift arithmetic. So for example, if you have a here is 5 bits, and we are shifting a to the left. Okay, so there is no shift. Okay, so shift arithmetic to the left is equal to shift logic to the left, but it matters when I shift to the right. Okay, 2 bit position, then I have to introduce the sign bit, which is here. Okay, so this is the sign bit. Okay, and have introduced 2 bits here as a shift to the right, shift arithmetic to the right. Now, concatenation means جمع bitat. It means this is a way of gathering bits. So for example, or variables. So for example, let's say I have here, so this is the operator. So let's say, for example, I have, this is B and this is the value of C. So this says add for me the bits of B and C and create a new variable. So here is will be what? So the bits of B is what? Is 0 0. Okay, so this is 0 0, and the bits of C is 1 0, and here is 1 0. Okay. How about here? Add A, B, C, and these 3 bits. So أعطيني A, which is what? Here's the A, which is 1 bit. This is the A. Okay, this is the A. All right. And what? B. Here is the B. 2 zeros. This is B. And C. 1 0. This is 1 0. This is the C. 1 0. And I need a D. D, which is what? 1 1 0. 1 1 0. Okay, this is D. Okay. All right. And and what? And 0 0 1 and 0 0 1. All of this I created them using this notation. Okay. Okay, and you can continue the last example. All right. Okay, and this is, we can get fancy with this thing. Let's say, for example, I want to repeat the variable 4 times A. So A is what? Is 1 bit. I want to repeat it 4 times. This is A, A, concatenate them and create a variable Y. I want to create 4 A's and 2 B's. So A, and the B is what? 2 B's. This is 1 B and this is 1 B, right? And then the same thing, add another C, which is 0 1 0. This is the C here. Okay. All right. So this is adding this replication operator is like how you gather variables and bits to create another variable. The conditional operators, this is an operator that we use in the assign statement that says uh, you have a condition here. You check it. If it's true, the result is this. If it is false, the result is this. Okay, let's take an example. The example would be a lot better. So here, for example, I'm going to check a condition. If it is true, then A goes to Q. If the condition is false, B goes to Q. Okay. So I can you can do this bit by bit as he's doing, by the way, here. Okay. Um, and we will see this in our coding, by the way, this condition operator, but typically it is used with assign. We'll get more examples as we get advanced, but as we discuss the data flow part of the language. In this table, we have this operator precedence, which means which takes first place in the evaluation. This is from highest precedence to the lowest precedence. And again, this will be evidence as you write more code and we see more examples. But for the most part, it is similar to what other languages are having. Okay, so this is the end of my uh, um, uh, presentation of this lecture. And I'm going to stop the recording here. Stop the recording.